Dorothy and her friends are determined to retrieve the broom, no matter how scared they might be. Blakely Tresca shares how to create light using chemiluminescence, because you can't be in the dark when you have light. Dorothy faces the hourglass of time, waiting to be rescued. Doug Williams conducts a series of experiments to show how reaction times can be changed. In the end, it is the Scarecrow who figures out how to melt/dissolve the Wicked Witch of the West using water. Julian Bauer has a much more believable way using acetone. When they return to the Emerald City with the broom, the wizard grants each of their wishes, even though they always had what they wanted all along. When he goes to take Dorothy and Trout home in his hot air balloon, it does the unpredictable by leaving without Dorothy and Trout. Chemist Renee shows us how balloons can be inflated by using carbon dioxide and explains why hot air rises as it does in actual hot air balloons, which doesn't happen with CO2, but does with helium. Just like her friends, Dorothy has always had the ability to go home. She just needed to be ready.
Hi, I am Blake Tresca. I'm a professor of chemistry at Kalamazoo College. And the demo that I'm going to show for you today is chemiluminescence. Chemiluminescence is a chemical reaction that converts chemical energy into light. And so the chemical energy that we're going to use is hydrogen peroxide. And that hydrogen peroxide is going to react with a molecule called luminol and introduce chemical energy into the luminol. The luminol will then take that energy and convert it into light. This is the same idea as a glow stick, and so this is a way that we can create light without any electricity and without any heat. So we'll be mixing two solutions. We have our luminol in solution A and our hydrogen peroxide in solution B. This also contains a catalyst, which is iron, and that's going to activate the reaction. So as we mix these, begin to observe blue light emitted from the solution. And now we can use this as our glow stick to light the way in the dark without the need for any electricity and without any heat.
Hello, my name is Doug Williams with the American Chemical Society, and I'm here to help you celebrate Chemistry Day. The National Chemistry Week this year of the American Chemical Society has the theme of making things go, or chemistry makes it go. Today we're going to learn a few things about how reaction rates can be controlled through various factors in chemistry. As a part of that theme, we're going to talk today about what makes reactions go and what you can do to influence the speed of a reaction. So with that, or to do that, I'm going to use some simple household chemicals to show you the things that you can use to make a reaction go faster or slower. Now, the first thing we're going to play around with is Alka-Seltzer. Alka-Seltzer is a household product. It's for indigestion. It's called an antacid because it has baking soda in it. It also has a little citric acid. And if you've ever done the experiment with vinegar and baking soda, you know that it forms a lot of fizz. That's carbon dioxide. And when you put the acid with the baking soda, that carbon dioxide fizz, if it's in your stomach, can produce some burping and maybe some kind of pressure and relief. Alka-Seltzer is a kind of a fancy product. It also has aspirin in it, so it's kind of a multi-purpose analgesic antacid. What I'm going to do today is show you how you can make the fizz in Alka-Seltzer either go faster or slower from the two reagents that are contained within the tablet. So we're going to open one of these, and these are just 2 tablet packets here that you'll see, and I'm going to show you the effect of temperature. First, we'll use some cold water. This has been on ice. Well, I have a little ice in there now. and some hot water in this thermos. And in between the two, I've got some regular room temperature water. And I want you to notice what happens to these 3 tablets as I put them in the different temperatures. We have cold, we have room temperature, or roughly 25 degrees Celsius, a little faster, and finally we have hot water. Obviously, temperature makes a difference in the rate of the reaction. This one's forming a much faster bubble, this one next, and the cold one is very slow. So temperature is an important factor. Another thing that we can do to make a reaction go faster is we can increase the surface area of contact between, in this case, the baking soda and the citric acid by breaking it up a little bit. So I'm going to use my hammer just to mash this up a little bit. And then I'm going to put this in and you see if it helps. This is room temperature water again, so we'll compare it to that one. Now we see a little bit faster reaction than we did over here in the first one. And so you can see that we can use a more finely divided reactant to make a reaction go faster. And finally, I want to show you what happens if you put in some more acid. In other words, going to increase the concentration of the acid. There's citric acid in the tablet, but we're going to add some vinegar, which I've already talked about earlier, or acetic acid. And you can get vinegar at the grocery store, keeping in mind that it's dangerous for your eyes, so you should actually keep a good pair of safety glasses handy when you're working with pure vinegar. Now my vinegar seems to be taking a moment to get started. And now you can see that this is actually one of the more vigorous steps, and in fact, I hope it doesn't overflow, but it is creating quite a lot of foam quickly. So we can do 3 things to change the rates of reactions. We can change the temperature, we can increase the surface area or contact between the reagents, and we can increase the concentration of those reagents. Those are 3 important factors. This, by the way, is the reaction that we're working on. It's sodium bicarbonate with citric acid to make the salt, sodium citrate, water, and carbon dioxide, if you are interested in the chemistry. Now I'm going to show you one more thing that you can do to make reactions go faster, and it happens all the time. In fact, you use what I'll call reaction enhancers in your daily life. If you are in the kitchen or if you're driving a car, there are things called catalysts that help reactions go faster. In the kitchen, you can imagine making caramel, and most caramel recipes have a little bit of baking soda. That's because the baking soda accelerates the reaction of the sugar and the fat molecules to make a good caramel flavor. If you did it without the baking soda, you could still get done, but it would take a little bit longer. So that's a catalyst. A catalyst doesn't actually change in itself during the reaction, but it makes the reaction go faster. The reaction I'm going to work on today is the decomposition of hydrogen peroxide. Hydrogen peroxide is used as a bleaching agent. It's also used as a sterilizing agent, and you've probably, if you have a swimming pool at home, you've probably considered or heard of people using it in their swimming pools to manage and keep the water quality up. Hydrogen peroxide for the pool is quite concentrated, about 30%, but if you're using it in a house to disinfect a wound or something like that, it's only about 3%. And so this is purchased at the pharmacy, or and you can pick it up. But it is inherently unstable. And I'm going to show you, even though I pour it out, it looks like water, but it's a 3% solution of hydrogen peroxide in water. And when I pour it out, nothing happens. Because it's generally stable for fairly long periods of time, but I could catalyze its decomposition. And there are some very dramatic ways of doing that. For example, if you put a material called potassium permanganate into this, it will foam very rapidly. And if it's a 30% highly concentrated form, it'll make a lot of heat. And if you put a little bit of dishwashing detergent in it, it'll make a nice foamy, big foamy tube that flows out of your flask. But that would be a little more advanced than today's lesson, which is just going to use this 3% version. So what we're going to look for when hydrogen peroxide decomposes is the formation of water, and what we can see is the formation of oxygen. So to do that, I'm going to use some yeast. And you can find this, most people who bake have this in their refrigerator. You take a little bit of yeast. It doesn't take very much of a catalyst to make a reaction go. And when you put the yeast in and swirl it a bit, it'll be a little cloudy. And if you look carefully, you'll see a lot of gas forming. All of a sudden, the oxygen is coming from the peroxide. And why is that? Well, yeast have evolved for millions or billions of years. And they have realized, these yeast have evolved over the years to prevent the oxidation that peroxide would cause inside of the yeast cell, and this would damage the yeast cell. So over millennia, the yeast have developed an enzyme that will decompose peroxide before it can do any damage to the yeast cell. At low concentrations, the peroxide is quickly decomposed into harmless water and oxygen, and the yeast survives. At higher concentration like this, however, the yeast probably don't survive, but their catalase is still working, and you can see it forming the bubbles of oxygen as it tries to decompose all of the peroxide that I put into it. So this is a reaction that because it's being catalyzed by an enzyme also explains how many things in your body work. Enzymes are used widely throughout your body to catalyze certain processes like the digestion of your food, and activation of your muscles, and many things that would help you metabolize and live very active and fruitful lives, which I hope you continue to do as you explore more chemistry. Thank you.
Hi, I'm Julie, and today we're going to talk about Styrofoam. You're probably pretty familiar with the Styrofoam cup. The Styrofoam cup is a good insulator. It keeps your coffee hot or your soda pop cold. And the reason it does is there's a lot of air in this Styrofoam cup. What we're going to do today is we're going to talk about what makes up Styrofoam, and then we're going to dissolve it. So Styrofoam is made up of a material called polystyrene. Polystyrene, poly meaning many, has many styrene molecules connected together into a big long chain. And that is what Styrofoam is made up of, all these styrene molecules. So we're going to disrupt this Styrofoam and dissolve it and see how much air is actually in this cup. So I remember I said polystyrene and the rest is air, a little bit of white coat coloring. So we'll put it into this thing here and we'll dissolve it, and you may be able to see that there's a white goop forming in there. And that's just dissolving that Styrofoam right into the liquid. And there she goes. So this big cup boils down to only this much goop. And if you take that goop and you dry it out, this is how much it is. So this cup was made from only this much material, and the rest is air. What we use to dissolve it is called acetone. Acetone is this molecule, and that's what goes in these in the liquid here. Is the liquid I'm using is acetone. It's very, very flammable. So if you're going to do this at home, be sure not to do it indoors, and be sure to do it away from any source of heat or flame. Don't leave the acetone in your garage. Think about that when you're working with it. So one question is, how is Styrofoam made? And what is it used for, other than Styrofoam cups? So Styrofoam is made by taking polystyrene and putting it in little tiny pieces into a machine that then adds steam to it. And those little tiny pieces blow up to about 40 times their size and create these little balls. And then those balls are then molded into whatever shape you want. These balls were molded into a flat sheet. You might be able to see the balls on the end of the styrofoam sheet here, all pressed together to make the sheet. So I said that styrofoam is an insulator because it has a lot of air in it. And that was a cool little demo. But let's see how much air is in this big piece of styrofoam. This is 208 cubic inches of styrofoam. That's quite a big piece, 8 inches by 26 inches. So let's see what happens when we dissolve that. Now you may be able to hear a sizzling sound. Can you hear that through the microphone? That sizzling sound is the air in the styrofoam being released as the styrofoam piece dissolves. And the acetone is getting a little trapped inside that white goo. So I was mentioning if you're going to do this at home, you need to think about safety. You want to have safety goggles on, protect your clothing, protect the surface that you're working with, because acetone dissolves all sorts of things. It dissolves lots of plastics. And that makes disposing the used acetone difficult. You have to think about how you're going to dispose of the acetone when you're working at home. So it's got to go not in a milk jug, but in something like an old paint can that's well sealed, or a bottle like this that says HDPE on the bottom. HDPE. And like I mentioned before, it's very flammable. I'm going to tip the tray a little bit so we can take advantage of the unused acetone. So here you can see that that big, huge sheet of styrofoam is made of only that much polystyrene. That's a whole lot less than that big sheet we had. So I mentioned to you that styrofoam is made by pushing things into a particular shape. Here's something that styrofoam is used for. Look at this fun guy. He's got lots of different nooks and crannies. What this is packaging material from a TV. The TV sits right in this slit here, and then it's got other places where they can put the manual and the remote, things like that. Why do they use styrofoam for packaging? Well, not only because you can shape it however you want it, not only because it's kind of cheap, but it's also very strong. So if you push on this styrofoam, it won't break. Well, it will if you give it enough try, but it pretty much won't break. So if the TV box falls off the truck and lands in the parking lot and it hits the corner of the styrofoam, it's not going to damage the TV. The styrofoam also absorbs the shock. The other thing that's kind of nice is it's really lightweight. So if you're going to package something in this much material, it's better to have something lightweight so you don't have to pay extra postage compared to something heavier. So what are some other things that styrofoam is used for? It's used for carry-out containers, and it's used for little packaging peanuts that aren't really as strong as that piece of styrofoam I just showed you. They're very light and fluffy though. These packaging peanuts are not made of styrofoam. They are biodegradable. Styrofoam is not biodegradable. And you can get carry-out containers and balls and plates and your egg carton. A lot of things in our lives are made of polystyrene. So here's a couple of other things that are made from polystyrene. There's a life jacket. It's light and it's waterproof, so they can put it in the life jacket and make a cheap life jacket. It's used in bicycle helmets. The inner layer of a bicycle helmet is made of polystyrene, and then they put a harder shell over it. The polystyrene in a bike helmet is the inner core. So take a look at your bike helmet, or go to YouTube and type in how are bike helmets made, and you'll see a cool video. This one up here on the top is a castle and a passageway into that castle. These are used in movie sets and film, TV, and theater, and it's a lightweight, cheap way to make the type of environment you want, like a castle, like this one. They just shape it however they want, and then they paint it. Another interesting thing that Styrofoam is used for is roads. Believe it or not, Styrofoam is under some of our roads. This is a picture of a bridge. The bridge is being filled with Styrofoam because if you fill that same amount of space with soil, the soil is expensive and it's heavier than the Styrofoam. So Styrofoam can be used in our roads underneath the asphalt and the soil that's put on top. And this is another cool thing Styrofoam is used for. It's used for surfboards. The inside core of a surfboard is made of Styrofoam. So they press the Styrofoam together, get it to stay nice and tight with each other to make it really dense, and then they start shaping it into the shape of the surfboard. That's another really cool YouTube video. So I've showed you that it's lightweight, it's durable, it's strong, it absorbs shock, which is why it's good in bike helmets, and it's very versatile. So polystyrene is in our world all over the place, doing all sorts of different things for us, everything from protecting our eggs to protecting our heads. So here we have the Wicked Witch. You remember the story from Wizard of Oz that you've been working with today? Well, the Scarecrow tried to melt the Wicked Witch with water in that storyline. We're going to do something a little bit different. We're going to dissolve her in this acetone. So we're going to set her in here, and we're going to see her dissolve. You can see she's dissolving away. Get her face a little bit wet. She's melting. She's dissolving. Sometimes the paint slows down the work of the acetone, so it's taking a little bit of time. And she is almost gone. Let's see how much is left. Well, there's a little bit there yet. Looks like the top of her head. So this was working a little bit better than water, wouldn't you say? The Wicked Witch is pretty dead. And now her hat is all that's left of her. The Wicked Witch is dead.
Hello, I'm Renee Bull. I work at Pfizer in Kalamazoo. My colleague Matt told you earlier all about acids and bases and how those reactions happen. Well, he let the gas go way up into the air. I'm going to trap it with my demonstration because we can't see gas very well, but this will show us that the gas is there from our acid and base reaction. So our supplies that we're going to need today are vinegar. You should have this in your house. It's diluted acetic acid. We have baking soda, that's sodium bicarbonate. So we have an acid and a base. We're going to use some balloons, a funnel, and a small spoon. So we want to take our balloon and put it on the end of the funnel, and then we'll take the spoon and put the baking soda into the balloon. I've already put the baking soda in here, so we're ready to go. Now we put the vinegar in a bottle. So this is just vinegar. I know it looks like water. Whew, it's stinky. That's vinegar for sure. So we have the vinegar in the bottle, our base in our balloon, and we put the balloon over the top. Now make sure you get an adult's help because sometimes the balloons can pop and this stuff gets everywhere. So be careful. We flip the balloon upside down and you can see, woo, all that gas is escaping away from the liquid and filling the balloon to make it go up into the air. That's that reaction that Matt was telling you about, pretty explosive. Now this balloon isn't the same kind of balloon as a hot air balloon or a balloon that you would see at the store that floats on its own. Hot air balloons use heat. This is a chemical reaction to create gas. Very different. And helium balloons that you get at the store, those have helium gas in them. That's a very special gas that's very light, and that helps carry the balloon forward. This gas, even though it's light, it's not that light. It doesn't raise up. You can see our balloon's kind of down a little bit. But it filled up. This captured the gas. You can see the reaction still going down there, but it was very quick.
You know I'm a dreamer, but my heart's a cold.
If you're ready to go home, repeat with us. There's no place like home. There's no place like home. There's no place like home.
I'm on my way home, sweetheart.
Thank you for joining us as we explore reaction times in this year's National Chemistry Week celebration of Fast and Slow, Chemistry Makes Things Go. And finally, a special thank you to Lydia Hines and the Kalamazoo section of the American Chemical Society for our 35-year Chemistry Day collaboration.
All stories come to an end, and so does this version of The Wizard of Oz. You have heard about lots of different types of reactions today, a number of which involved indicators. Here we will spray the indicator phenolphthalein on 2 words, which I'm going to write on a white piece of paper with a solution of sodium hydroxide. That's a base. Let's see what happens. See the nice pink color? Have a great rest of your day. And remember that your bodies are amazing chemical manufacturing plants, created and designed to do chemistry all day, every day.